Yeah. Hello, everyone. I'm Nishit. I'm currently in my final year at BMS College of Engineering. So, yeah, democratizing silicon sounds a little daunting, doesn't it? And yeah, one more thing. I know, it's nearly 4 o'clock. Many people are out of energy, but I would need some responses from you guys to have a good presentation. This is the first time I'm presenting, so thank you. So, yeah, uh, first of all, we are at open source community, right? We all have seen a lot of open source softwares, but that raises the question that why do we need open source hardware? So, whenever I think of chip design in first year, when I heard of chip design, this was the first chip design that I thought it was. So, I mean, even this is open source now. If you have we have people from FOSSI who have OpenCFD. Yeah, like open source is everywhere. But when I was trying to search in my second year, like where are the chip design initiatives which are open source, it was very hard for me to find any very important resources. The main reason being not many people know about it because the industry has good hold, and it had kind of a monopoly in that sense. Similarly how software was, just imagine, uh, we had Solaris and people stopped at Solaris and thought, why do we need to have like, yes sir. And why do we need open source software? Why do we need Linux? I mean, if you have a problem, I'll just call Solaris or RHEL. They can sort it out. But the motivation didn't end there, and we have a whole open source ecosystem everywhere we need. Similarly, the chip design. Uh, so this is basically what chip design looks like usually on silicon. These are roots, and half of it is copper, half of it is SiO2, which is nothing but glass, and rest of it is silicon. And it seems very daunting to think you can design it, something that runs everything, right? So when it comes to such topics, there is a first question that comes to our mind, which is why? Why do we need open source? Mm, So in chip design, one thing open sourcing is it allows you to have a open, like you know what works behind the doors, right? Unless and until you know what works behind the door, you can't have a very good hold on what you want to do. Let's imagine a situation. There's a country A and there's a country B. Country A has good resources, but uh, good software, but not very well learned engineers. Let's imagine there's country B where there are people with lot of skills, but not enough resources. So country and country B have a mutual exchange of resources and skilled person. But imagine due to some geopolitical instance, country A decides to stop its resources reaching to country B. Even though country B has the skills, it will never have the ability to do anything. For example, in chip design, they won't be able to have a chip. And for a twist, let's think there's a country C, which has resources but has low skills. But without the software licenses, there is nothing that country B can do to maybe, for example, make a chip, right? So that's where open source plays a huge role. Where they have a completely openly sourced ecosystem for chip design. The only hindrance is your physical resources. And there are some ways where that can be managed, and open source is getting a huge good rep now. So this is what we call the open source VLSI design flow. The first thing is system specification. So as every system is designed, you have certain specification that you need to hunker down so that you have an idea of what to do. Then there's architecture design, which is creating the architecture which is suitable for your application. For example, you have to add two numbers. We have something known as adders, right? There is half adder, there is full adder, there is carry look ahead adder. There are many flavors. You can choose one which fits your use case the very well. Then there's functional design and logic synthesis. So this is one of the most important part. This is where you know that your logic works. You run it, you functionally test it and see how it runs. Then there's of course circuit design, which is the one of the hardest part to do because it takes multiple iterations to get it right, and you have to get it just right so that it, like, you will have a certain of a amount of maybe area or power buffer, but if you exceed it, of course there will be physical damages to a circuit. Then there's physical design. So this slide, this is basically how physical design looks. This is basically what you print on a silicon. You have like, it's, you need to have a good understanding of material sciences for it. There are like thousands of materials that are used currently. Recently there is something known as SOIs, like you put insulator or semiconductor to make a transistor. Then there is physical verification, because all the like whatever printing methods we have, like yeah, I hope you guys know about TSMC, Taiwan Semiconductor Manufacturing Company. There is ASML. So these all are the part of the printing ecosystem, the PD ecosystem. So yeah. Then there's fabrication, where uh, of course you have literally printing your design on silicon and making it functional. Then there's packaging, testing, and then you have a chip. So in open source silicon, there's one of very big institute, which is JKU, Johannes Kepler Institute, University. So they have compiled a Docker container with all the tools that are required for open source silicon design. So there's a QR code if you want to the GitHub repo. Yeah. So when it comes to open source design, the biggest problem is standardization. The industry tools have very good standardization. So, for example, I'm sitting in India and I have a friend in USA. I want to communicate a design to him. There's a parameter called DBU, which is database units. So it's basically how you define how what your length and width of your semiconductor blocks are. So if I'm having my system in maybe 1 nanometer and he has us in 5 nanometers, it might work well, it might look good, but once you get it fabricated, it will never work, because there are like millions of parameters that change between 1 nanometer to 2 nanometer. Yeah. So my experience with open source tapeout was, there was a chipathon held by IEEE SSCS. So they had given us an idea to tell us like use open source tools only to make a chip. So we made something known as PGM, which is programmable gain amplifier. So amplifier is anything which amplifies your input. Programmable is the part where you have 3 digital inputs, which you can like, you can use binary, like you can turn 3 switches, all 3 on, you'll get the highest gain, lowest, and so on. So this was a circuit. You were 3 people. It took us 7 months to get it done on open source, all thanks to non-standardization. But yeah, but in the process, we learned so much which goes behind the hood, and I probably all the 7 months were worth it. I missed my internals for it, but it was worth it. Yeah. So this is what we call physical design. This is from a software called KLOUP. So that part, right? That's transmission rates, and that's the resistors. This is the heart of a PGA, and this is the OTA, which is the just mainly the amplifier. Yeah. So yeah, I told like this design is getting taped out. So probably by next March we will have it on a working chip. But yeah, testing needs to be done after packaging. Let's hope it works. And more than that, there are many other places where open source chip design has played a role, and it has made something which a lot of people use. One is this. This is OpenTitan. It works on something known as ROT, which is root of trust. I'm not sure if you guys have heard. Like there have been rumors or conspiracy theories. I don't know why to put it, but people say there is the management engines which are on CPUs are also like the data collecting using BIOS systems, and like there are a lot of stories. So a team of people decided to just create a CPU with open source, because closers they didn't have enough money for it, because licenses cost a lot. But like, because usually such softwares are used by huge industries, so it's not worth it for a single individual to buy a license. So they decided to make a whole CPU. It took them like a long time, but yeah, it does work. And this is based on RISC V. It's very close to what we have for ARM. The architecture is very similar, but pretty different. So even people are now thinking to shift from x86 to our RISC V's, because ARM has its own inherent advantages, and both of us work on RISC framework. RISC is the reduced instruction set commands. And this is from a there is something known as PDKs, which is process design kits. So when you have a design, it needs to have certain um, internal blocks which have to. It's like playing with Lego. You have a predefined blocks. You connect them in certain way in which you want them to behave. So there's a PDK called Sky 130. There is IHP. There is GF 180. There are 5 or 6 open source PDKs, not in very small nodes, but they go until 75 nanometer nodes, if I'm not wrong. So this is one of such nodes, which is from Skyward 130 nanometer. So this is literally how a semiconductor fabric, like a wafer work, looks. So these each part is what will go in the system. It will be packaged, and yeah, we were probably in some systems which are working right now. Yeah. So what can we do as people? First thing, you can just learn a little, little bit of electronics. I mean, it takes some time and patience and courage, in a way. But yeah, movie one 10, 20 years ago, there wasn't such good open source ecosystem for it. There is no good support. There is good documentation. There is good maintenance. So I guess we all can take a try. It's not necessary to technically contribute to it. That the contributions can be towards documentation. You can just this is how I'll contribute. I'm just telling you all people. You'll tell some 10 people. So hopefully it will spread. Yeah. So these are the resources we want. This central QR code, it's from eFabless. Have you all heard of eFabless? Yeah. So they were one company. I won't like to tell that they are a company, but they had something of shuttles where it's like shared real estate. Like there's a huge land which we all can give money and take parts of it. They did the same thing with wafer. The semiconductor wafer making one costs a lot. So what they did was they pieced it, they sold it like real estate. They made a small margin out of it, but yeah, it helped out a lot of freelancers to have their own tape outs. Yeah, so it was later acquired by Chip Foundry. So the company isn't like functioning right now, but even Chip Foundry does the same thing. So it's one in the same thing. And this is my team's PGA tape out. You guys can have a look. And that's all the tips that you would need for Opal's chip design. And yeah, thank you. And if there are any questions, please, if you want to look at a meme.
So, thank you for your talk, Dishit. And is that PGA, right?
Yes,
Yeah. So, one thing that came into my mind was like, when we do amplification, right? What about the noise cancellation? Because how do you deal with it? Like, how do you deal with a rogue signal or some signal which is distorted and which can contribute to noise? How do you deal with cancellation of it? Like, how do you make sure that doesn't get amplified?
So, when it comes to an amplifier, selectivity is not the option. So, what we do is we create another feedback circuit.
Okay.
And we employ negative feedback.
Okay.
The gain, like we have two types of gain, which is closed loop gain and open loop gain. Yeah.
Yeah.
Open loop gain will always be high than closed loop gain.
Yeah. Yeah.
Because in closed loop gain, now we are employing negative feedback. But the plus point is whatever the rogue signal, the noise is, it will also be subtracted out during negative feedbacking.
Okay.
Yeah.
So, another point is like when you apply feedback and when you run multi-page systems, or let's say like all of production on some sort of solution. how about the temperature? When the temperature rises, the thing is the performance goes down.
Yeah.
So how are you tackling the trade-off?
The trade-off again depends upon the range at which the amplifier is working, of course. But again, it doesn't vary until the temperature reaches very high. Until then,
Let's say, for example, uh, system gets unstable like between 50 to 70 degrees. For example, in an SOC or something like that. So how do you control the parameters here? Like they are cascading and dependent on each other, right? Yeah. So I'm really interested in mind, but
uh, as of now, I'm not aware of how to control the trade-off. Probably I will have to read about it. But as far as I remember from my analog design classes, the cascading usually helps you with the parameters because each amplifier has its own selectivity, right?
yeah.
So when the parameters go out of range, it just rejects it.
Yeah, okay.
So that rejection causes this amplifier to shut down, and it cools down and brings it back to the swing region that which it operates in usually. But there might be some compensatory circuit structures which can be used to track these two.
Yeah, we'll take it off like that. Yeah, sure. Yeah. Okay, thank you, Nishu.
Thank you. Any other questions? Yeah. Fine. Yeah. How's the name? Yeah, QR code. Yeah. Yeah, this is a QR code. No. Because the one thing about fabrication is it's not a single it's not a single industry. It's like two raccoons having the same trench coat. It's like thousands of raccoons having the same trench coat because you need material science, you need electronics engineering, you need software, you need even electricians, you need plumbers, you need chemists, you need biologists because many of the foundries have like very harmful wastes. You have to take care of that. Like it has too many industries to in one place to make it open source because it takes a lot of industry like initiation for it. But maybe one day if 10 of each of all industries come together, maybe we could have something. You never know. Maybe sometime in the future. Yeah, maybe sometime you can start something, man. Hopefully I get taped or something from you. Any more questions? So these are the QR codes. Like I was thinking I would have demo, but I like saw this video and I was like I could never be as good as that. So yeah, better resources for you guys. And yeah, that one QR code will have all the necessary tools that you have. So just try experimenting, just see where it leads. There are good documentation for everything. And if you don't have, the maintainers are really helpful. I personally contacted them. So good luck. Thank you.